Continue recording. Okay, we are recording. Great. Good morning, everybody. I'm very happy to start this new semester with you. Today is going to be quite tough for me for two reasons, actually. One, that I never tried to lecture with a special pen on the screen. So for me, it's an experiment. Hajac tells me that one can get used to it and improve with time. I hope it will happen with me. And another thing is that, especially for today, for you, I proved a very nice theorem. And because of it, I didn't sleep a single minute. So I feel a little bit like a zombie. So please be patient with me. For starters, let me give you some statistics. So there are 25 of you, and 8 are from the previous semester, 17 are new. Out of you, 20 are students and 5 are professors or postdocs, whatever, but with a PhD. And 6 are regular students who will get a grade on USAs. Okay, so that's statistics. And because of the 17 of you who are new, I have to repeat some basic stuff from the previous semester, just that we are on the same page. I really apologize, the 8 of you who know it by heart. I remember Davide in his review of my lecture course, he said that he had the definition of graph, directed graph, given 4 times during the previous semester. So this is kind of painful to hear the same definition over and over again. It's not so much as I want to explain a definition. I assume that all of you are familiar with it one way or another, but I want to introduce the notation. We must be on the same page. And yes, I'm jumping straight into path algebras today, no longer pure graphs, so don't worry. But I need a few good concepts and actually notation for these few good concepts so that you understand what I'm writing. And to save time and not to spend too much on recalling stuff, because it was another remark of students from the previous semester that I spent too much time on repeating things. I'll try to avoid this mistake. And I will try to speed it up, but some things I have to say to begin with. Okay, so this time we are going to do really graph algebras, not just graphs. And I want to do it in a systematic way. So I don't want to jump immediately into sister algebras, analysis, some inequalities, and so on and so forth. Because we can do it in a far more systematic way, understand its algebraic roots. And the way I think is most systematic to do it is to start with a very, very important and ubiquitous, omnipresent in mathematics concept of path algebras, of a directed graph. That's something which is heavily used in representation theory, in classification of finite dimensional algebras. So that's something in mathematics for its own sake. It's not just because of what we are doing with Levitt path algebras and graph sister algebras and uncompleted topology. It's important on its own right. And then from path algebras, we have a very natural path to Levitt path algebras. And then we can view graph sister algebras as the universal enveloping sister algebras of star algebras, which are given as Levitt path algebras. And it's a lot of fun to explain how axioms that were written by people who introduced graph sister algebras much earlier than Levitt path algebras were discovered. It can be rephrased in this more path algebraic way, which is actually more user-friendly because it's definitely nicer to have equalities than some spectral inequalities. It's inequalities of projections are less nice to handle than, say, some equalities of generators, of combinations of generators. And when you can prove that the things are equivalent, this is a much better setting. When you want to check that something is homomorphism, so it satisfies relations, it's better to have relations given algebraically. And it's really nice that at the highest level of generality, all these graph sister algebras can be written as the universal sister algebras of Levitt path algebras, where all relations are given by algebraic equalities. Okay, so this is roughly the plan for the whole semester. Of course, we want to prove some important theorems in this context of Levitt path algebras and graph sister algebras, theorems that are relatively new, just got published, and that are very strongly motivated by non-commutative topology. So that next year, hopefully, we might go into K-theory and doing something even more serious with it. But let's begin. What is a graph? Well, to begin with, when we say a graph, we mean a directed graph, not an undirected graph. And of course, this is a matter of choice. If you are mostly talking about undirected graphs, then you call undirected graphs graphs. And when you want to make an exception and speak about a directed graph, you say directed graph. But we are in the opposite situation. The graphs we are talking about are all the time directed. So we abbreviate it just to graphs. And whenever we would need to speak about an undirected graph, we would call it an undirected graph. And for me, it's a bit of a shame that in this context of graph sister algebras and Levitt path algebras, actually people use this word graph, because there's a beautiful word quiver, which is used by people who do path algebras actually, and classify finite dimensional algebras and representation theory, which is called a quiver. This is a very beautiful word. This even has a nice name in Polish, kołczan, and you say arrows instead of edges, and somehow you don't have to say directed, because when you think about an arrow, of course it's directed, and when you think about a quiver, well, this is a collection of arrows, so that all makes sense. But that's not used in graph algebras, and that there's no way to change this terminology, so we have to stick with it. Okay, so what is a graph? A graph is a quadruple. We have a set of vertices, we have the set of edges, also called arrows, and then we have two maps. Both go from the set of edges to the set of vertices. One is the source map, which assigns to our edge its beginning, and one is the target map, or also called the range map, which assigns to an edge its end. And I just want to alert you to this notation because I'm going to use it all the time. So I use the superscript 0 for vertices and superscript 1 for edges. And I use superscript instead of subscript because every now and then I'm going to use graphs E1, E2, and so on. And then I will number graphs with subscripts. So sometimes we'll have two indices, say E01, meaning that I have all vertices in the graph E1. Okay. And S and T is now my reserved notation for the source and target. Okay, so that's it. Now, what else we will need? What I need to recall? Yes, we will need the concept of an intersection of a graph. And well, it looks pretty obvious. But there is one slight subtlety. If you have two randomly given graphs, it's not always true that their intersection exists. It might happen that their intersection does not exist. So what are you doing to get the intersection graph? Well, of course, we have to intersect respectively the sets of vertices with themselves, the sets of edges with themselves. But it might happen that when you restrict the source and the target map from F to F intersect G and from G to F intersect G, these restrictions do not agree. And if they do not agree, there is no intersection graph. Okay, so that's the condition actually, right? We must have it that if I restrict my edges to the intersection, then the source from G and the source from F agree, and the same is true about the target. And when they agree, well, I call then the restriction to the intersection S cap or T cap, respectively, and there exists an intersection graph. But the good news is that once the intersection graph exists, then also the union graph exists. Here we go. Right, because now we have a similar situation. We take the union of the sets of vertices, we have the union of the sets of edges, and now we have to define S cup and T cup. Before it was S cap and T cap. Yeah, I know it's very subtle to hear the difference, but one is cap, one is cup. And so yeah, the cup's like a cup of tea. And now, of course, if we want to have a consistent definition, then again, we must have that the source of f and source of g agree on the intersection. And if they agree on the intersection, there's an obvious way to define the source and the target maps on the union, right? Because if I take any edge which is in the union of the sets of edges, so any edge in the union graph to be, then I declare that this S cup is defined as f of E if E is in F1. Oops, I didn't mean it. What happened? And as G of E if E is in G1. But of course, it might happen that E is both in F1 and G1, and then they have to agree. Otherwise, this definition doesn't work. And of course, the same for T cup. So you see that if the intersection graph exists, then also the union graph exists. And we'll need these concepts today. Okay, what's next? I'm not sure I skipped it. I need subgraphs are pretty obvious. I'm not going to define it, but I want the opposite graph. I will use it today. It's a very useful concept, especially for opposite. Yes. Okay. So whenever you have any graph, we can define the opposite graph. And the opposite graph has the same set of vertices, the same set of edges, but the source and the target maps are interchanged. Okay, so we say that the source in the opposite map is in the opposite graph is the target in the starting graph, the initial graph, and the target map in the opposite graph is the source map in the initial graph. Okay, so basically what you are doing, if you want to visualize it, it's very obvious. We are just reversing the direction of the arrows. Okay, and that's very important in graph history algebras, like algebras. Okay. Next we need the concept of a path. Yes. Oops. This computer is a bit jumpy. No. Oh, yes. Okay. That's what I need. So I have a graph, and what is a finite path? Well, the finite path is either a vertex or a finite tuple of edges, say from E1 to En, with the very important condition that the end of an edge is equal to the beginning of the next edge. So T of E1 is S of E2, T of E2 is S of E3, and so on and so forth. And finally, T of En minus 1 is equal to S of En. So if I take any two adjacent edges, then the end of the first edge must be equal to the beginning of the next edge. This is a very obvious definition. And we now can easily extend the concept of the source and the target map from the set of edges to the set of finite paths, with the obvious understanding that well, if I look at the vertex as a path, then of course the source of the vertex is a vertex and the target of the vertex is a vertex. That's kind of obvious. There's nothing more you can do. And if I have a path like this, Pn, then the source of Pn is just the source of the first edge E1, and the target of Pn is exactly the target of the last edge En. Okay, so I think this is written somewhere here. Okay. And sometimes without changing notation, we use the same letters to denote now maps, but on a much bigger domain. Sometimes you have to be very careful with notation because you take pre-images. And take pre-images, I mean, you better specify the domain because otherwise it's completely confusing. But by default, if I'm not specifying what I mean by the source and the target map, I always mean it in its canonical sense, notably a map from the set of edges to the set of vertices. Okay, and when I take pre-images, but of course when I have S of a path and T of a path, then I mean it's extended to this larger domain. Okay, what else do we need? No need to talk subpaths or infinite paths. Yeah, we will need the concept of loops. today. And here I have to warn you that terminology is not very consistent. Some people say a cycle instead of a loop. I just don't like it too much. I like the word acyclic for a graph without loops, but somehow I was never convinced that using the word cycle is a good one. Luckily, this word cycle is more used by people who do path algebras rather than graph sister algebras. The word loop is more common in the realm of graph sister algebras, so let's adopt it. And we call a path is called a loop if it is not a vertex. So vertex is never a loop. And we have that the end of a path is equal to its beginning. Okay, so if P were a vertex, this condition would be satisfied, but we never call vertex a loop. Okay, so a loop is always at least of length 1. Well, I haven't defined length yet, but it's coming. Okay, and well, at a certain moment, we'll need to know what it means that a loop is vertex simple, but not today. What it means that it has an exit. This is very important in graph sister algebras. But I don't know why I wasn't using this terminology in the previous semester. A graph is called acyclic if it has no loops. This is very convenient. I was all the time writing it has no loops, it has no loops, it has no loops, but you can just say it's acyclic. And this I like, yeah. That's a nice abbreviation. So we're going to use it today. Pointed paths, not today. Related, unrelated, not today. I still need the length of the path. We'll definitely need this theorem. It's an elementary theorem, but we did it as a warm-up. I really don't understand how this computer works sometimes. Okay. Okay. So let E be a finite graph. Now, what do I mean by finite graph? Of course, I mean that both sets E0 and E1 are finite. Okay, not just one of them, but both. By the way, we are not assuming it unless necessary, but I've never seen E0 or E1 being more than countable. But I think that at least Anya, you attended this lecture by Soren Ehlers about classification of graph sister algebras, and I asked him this question: I mean, how about graphs that have uncountable infinities? And he said it's not excluded, but it's basically nobody studies it. Okay. But we don't want to completely exclude it. I mean, there are sister algebras that are not separable, like there are non-separable Hilbert spaces, and then they are useful sometimes. So I don't want to dump it unless I need it. But of course, I'm not aware of any interesting examples where we would have uncountably many arrows, I don't know, shooting from one vertex. Yeah, but it's not excluded. So for as long as we don't have to assume countability, we don't assume it. Now, yes, I think that we passed this concept of a length. So I have to back up a little bit. This is a loop. Yes, oh, sorry, it was just above. So I don't need it anymore. Okay. So we think about vertices as finite paths of length 0, and the length of a finite path, which is not a vertex, is the size of a tuple. So when our path is just a sequence of edges E1, E2 up to En, with a condition that make it a path, then the length of such a path is N. So this is a very obvious definition. It's just the number of edges you use to have your sequence is the length of your path. Okay. And we will need it today. And I think that the rest can be done later. There is a number of other things we are going to need, but not so immediately. So I prefer now to switch into whiteboard. Just have to figure out how I do it. So I suppose I'll stop sharing. I'll start sharing again. But now I'll do the whiteboard. Yes. Okay. Full screen. want to bring it down a bit. Yes. And I have to pick up my magic pen. I forgot to pick that. You know that the pen is $100, but $400. That's crazy. Okay. Desk I have here is slightly too small. And I'm all the time under the name of Jarosław Gowin. It's never changes. Okay. Right. So clear your all drawings. So now we start with this beautiful new theme of path algebras. Is brown okay? I can change the color, but and I think we will spend 2 lectures on path algebras. Probably not more, but I think 2 lectures are fine. Okay, so for starters, how do I create an algebra? First, I need to have a vector space. By the way, Anya, I will ask you for the recitation class next week to do algebras, rings, modules, such stuff in general, okay? But I don't want to waste my lecture time for this. So let V be a vector space. I also will try to avoid writing full English sentences. Just I will speak and write formulas or some abbreviated stuff so they understand what is what symbolically. But I think it's a mistake with my horrible handwriting and the awkwardness of using a digital pen. I will try to be comprehensible, but I avoid full English sentences. So the vector space, you have full English sentences in the lecture notes over some field K. But I'm not assuming anything about this field, okay? So it can be characteristic to whatever, you know, can be a finite field. Of course, when we will go to graph system algebras, we'll take our Leavitt path algebras over complex numbers, and then we will use the concept of the opposite quiver of the opposite graph as a concept of star operation on our algebra over complex numbers. But we are not there yet. Okay, so I have a vector space over field K, and how do I turn it into an algebra? I need a bilinear map. Oops, but not with an eraser. I need a bilinear map from V cross V into V. Let's call it M. My linear map satisfying just one condition, the associativity conditions. Condition. And again, like with my remark about directed graphs versus undirected graphs, again, you can speak associative algebras versus non-associative algebras. Since we are doing all the time only associative algebras, I'm not going to say associative algebras. For me, algebra is always associative, okay? Just like for me, graph is always directed. That's just not to use all the time a redundant word. And this is quite common, actually, but one thing I really want to alert you to, especially people more in algebra than analysis, is that we are never, ever going to assume unitality except when explicitly spoken about, okay? So when I say a ring or I say an algebra, I do not mean a unital ring or a unital algebra, okay? I'll always highlight a unital algebra or unital ring when it is unital, okay? Although most of our examples and motivations are unital, and we'll devote some time to the concept of unitalization. That's an interesting concept. It's like one-point compactification of a locally compact Hausdorff space to a compact Hausdorff space. So that's this is an important and interesting stuff, and we're going to do it. But it's very important for us not to assume unitality, because we have nice examples. If you take, I don't know, all finite dimensional algebras, M infinity. This is not the unital algebra. If you take the sister algebra of compact operators, it's not the unital algebra. And it would be a shame not to have such examples, okay? So I'm definitely not going to assume unitality unless really necessary or just given in my examples. Okay, so if you just have an algebra which is not necessarily unital, all you need is to have a bilinear map from a vector space V cross V into V. This takes care of distributivity law, and you need just the associativity condition, okay? So in order to create a path algebra, I first must give you a vector space, okay? And here is going to be a very important line I'm going to write. So let E be any graph. We define that K E, it should remind you of group rings, okay? So if I would have E being a group, then I would write KG, and this would mean group ring, okay? So here, instead of a group, I have a graph, and it's kind of a similar idea. But I want to define it pedantically, the way it really holds water. I don't want to make any shortcuts. I want to be really thorough and systematic. So I'm going to write something which might look a little bit redundant to people who have experience with Leavitt path algebras or graph sister algebras. Namely, I'm going to define this vector space as the space of all finitely supported maps from the space of finite paths of a graph E into our field K. All right. So this is going to be all maps. And I didn't introduce this notation, but okay, I'll do it right now. Yeah, I was supposed to highlight it and I forgot. So you see, whenever I have a graph E, by FP of E, I mean all finite paths in E. Okay, that's obvious. I define two finite paths in a graph E, so I really take the set of all finite paths in E. Okay, and that's an eraser. And I take all maps from, no, don't clear jobs. From FP of E into my field K, but I want them to be finitely supported. So I write it that these are such that F of P is not 0 only for finitely many P. Which are, of course, paths. Okay, so please bear it in mind, because this is a very important line. This is my vector space on which I'm going to define an algebra structure. Okay. Now, can I go to the next page without erasing this one? Does anybody know how to do it?
Okay. Yes, Professor. Bottom to the right, there is something small. You can.
I have saves, yeah?
It will be saved, yes. I mean, this
as PDF.
Well, I don't know. At the end of the day, you could save it as a PDF or as pictures,
Yeah.
as the the lecture is finished. But for the next page, you can you can go to the bottom and right part, as you see. There is some small square, can you see? With a plus on it.
I see something which looks like kill everything button. That's probably not it. I have a save, I have redo, I have undo, I have format, eraser, spotlight, stamp, draw,
Oh,
text.
on
No.
bottom right part, can you see? Right button.
Right button. But this is a cross. If I press it, I will kill the bar.
No, it is not a cross. It is a square with a plus on it. I can see it from here. I mean, I can see your. Can you see here? I write here something. Can you see?
Ah, yes. Okay. Yes. Sorry. Thank you so much. Yes. Okay. Thank you, Anya. Yes, because I was looking for it on at the wrong spot at this black bar. Yes. Yes. I warned you. It's my first time.
No.
Okay. Good. So now we are going to define this bilinear structure, but first I want to observe what is the basis of this vector space. It's completely obvious. These are characteristic functions for a path. So let me write it down. The set of all functions chi p, where p is a finite path, even by the chronicle delta. So chi p of q is equal to delta pq. So chi p is an element in ke. Okay, so this I can write it down. This belongs to ke. It's a finitely supported function on the space of all finite paths. Okay, and in fact, it's supported on just one path, notably p, which is its index. Okay, so this is equal to 0 if q is different from p, and is equal to 1 if q is equal to p. Okay, and this is a basis, the set of all such functions, where p runs over all the space of all finite paths, is a basis of our vector space ke. Okay, that's completely obvious. But still, let's verify it. So I want to show first that an affine supported function is spanned. So indeed, let f be a function, so k of e, with the support. Since it's finite, I can enumerate it. Let me write it down as q1, q2, qn, where each of these q's is just a finite path in E. Okay, and this is our support. So now I claim that then I can write f as the sum from I equal 1 to n of f of qi chi qi, right? And this is because if I take absolutely any path p, then f of p, and now I substitute, this is equal to the sum from I equal 1 to n of f of qi chi qi of p. But remember, this is just Kronekrol's delta. So p is just one path. And now, well, I have to write the braces. Maybe I'll call this support capital Q. Okay. So of course, I'll just get 0 if P is not in Q, right? Because if P is not one of these paths Qi, then this chi Qi of P will always be 0. The sum of zeros with any coefficients is 0. So it's going to be 0. But if P is in Q, then it means that P is equal to Qi for some I, right? So this is just, this will be 1, and I'll get just S, I'll get F of Qi if P is equal to Qi. And that's it. It agrees. So this is really F of P for any P, because on one hand side, that's just a substitution, right? I'm computing what is this function evaluated at any P, and I see that it's 0 or F of Qi. But if of course P is equal to Qi, then F of Qi is equal to F of P. All right. So I have two cases. If P is in the support, then F of P is equal to F of P. Everything agrees. And if P is not in the support, so P is not in Q, then F of P is equal to 0, and what we compute is also equal to 0. So if two functions agree on all elements of the domain, the functions agree. So this is the spanning property. Now I know how to do it. Go to the next page. And now the linear independence, that is also elementary. Let's so let me just summarize. So hence okay, E is the span, the linear span of the set chi P with P running all finite paths of E. Now we need to prove the linear independence. So let's take any non-empty finite subset to show the linear independence. Take a non-empty but finite subset. How do I want to denote it? Well, these are just some chi's from P1 to Pm, okay? So chi P1, chi P2, dot, chi Pm. And of course, this is a subset in the set of all chi's with P running all finite paths. Okay. Right, and now we test the linear dependence. So what do? We write the equality that 0 is equal to the sum of alpha I chi pi, with I ranging from 1 to m. And of course, this is a function, so a function is equal to 0. If it is 0 or any path P, well, yes, on any path P, so in particular, it must be 0 on any of these paths Pj, where J also ranges from 1 to m. Why did I write such a curly brace? Okay, but of course, when I evaluate it, I'll get Kroneker's delta, and this is just equal to alpha I. So that's just the linear dependence. Okay, that's done. So indeed, this set, this one, is the basis of KE. All right. Yeah, and now I think we are ready to define the multiplication. Any questions so far? I think it's completely elementary, right? Okay, so maybe I'll go to the next screen. So we have our vector space KE, we have a natural basis given by characteristic functions chi, and now we want to define the bilinear map. And of course, when I define a bilinear map on the vector space, it suffices to define it on all pairs of basis elements, right? So we will use this basis to define a bilinear map. Let me call it M from KE cross KE into KE. And I take M of, I want to change the notation. Okay, chi P and chi Q. And now I must define some element in the vector space K of E. And by definition, I take it to be chi PQ if the end of P is equal to the beginning of Q, and I take it to be 0 otherwise. Okay, so this formula defines a bilinear map from the vector space KE cross KE into the vector space KE. And now to make sure that this is an algebra, all that we have to verify is the associativity condition. And this we can write as a proposition. And also, I mean, this should be very intuitive to what's going on. If you ignore my formal notation with functions and so on to make it rigorous, you can just think that you are simply decorating paths with some numbers. And when you multiply paths decorated with numbers, then you multiply the numbers, and then you multiply paths by concatenation. So if the end and the beginning agree, then you create a bigger path, and if they don't, that's just 0. Okay, so if I have a path P here, sorry, this was Q, and a path P here, so the end of P is not the beginning of Q, they multiply to 0. Okay, but if it happens that P ends where Q begins, then multiplication of these two paths is the new path PQ. Okay, so this is a very intuitive definition. And now I can make the claim proposition. The bilinear map defines an algebra structure KE. The bilinear map M defines an algebra structure on KE. And the only thing we need to do to prove it is to prove the associativity condition. And of course, because we have this nice basis of characteristic functions chi, it suffices to do it on triples of characteristic functions. Okay. So, proof. First, I need to compute. So you see, I'm skipping all these words. I'm saying them, but I'm not writing them. I'll just do the calculation. But it's obvious what I'm doing. I want to prove the associativity conditions for all elements of KE, but because my maps are bilinear, I can always take away all these coefficients. And at the end of the day, I'll be verifying things just on basis elements, okay? So I need to first compute. I take 3 arbitrary paths PQR. And first I compute M of chi P, comma, chi Q, and then comma chi R. And it better be the same thing as M of chi P, comma M Q, comma chi R. Okay, but first let's compute it. I mean, maybe the word compute is a bit too strong for such an elementary play, but what I'm doing, just verifying. No, I wanted this. Sometimes I make some random marks. Okay, so what do we do? Well, I just, here I plug in my formula. Okay, and remember here are 2 cases. So I also must write 2 cases here. So one case is, remember, this is just M of chi PQ, comma chi R, if the end of P is equal to the beginning of Q. And of course, 0 otherwise, which means when T of P is not S of Q. Yeah, but now I can still write it down explicitly. What is this M of chi PQ chi R? So this is equal to, and I will have 3 cases. You see, when the end of PQ is the beginning of R, then we'll just have chi PQR. And of course, I'm using the associativity of concatenation of paths, right? I think it's obvious. When I have a path P and a path Q and a path R, then of course I can say, aha, so first I'm taking path PQ, and then I'm taking path PQR. But of course, this is exactly the same as taking first, sorry. As taking first QR and then putting P at the beginning, all right? So that goes without saying by the definition of a path. There's nothing to check, it's a tautology. Okay, so let me erase it. What is nice with this whiteboard is that there is no chalk dust. I was always completely dirty, and then my glass would go to pieces after a lecture. And that's more convenient. Okay, so this is chi P. Oops, cannot write with an eraser. P Q R. When what happens? So first, this condition still holds. So we must have TP equal to SQ. But now we have another condition. We must know that the end of PQ, but the end of PQ is the end of Q, is the beginning of R. So, and the end of PQ, which is the end of Q, oh, darn. No. Okay. Is equal to the beginning of R. Okay, so now I have 2 conditions. TP equals SQ and TQ equals SR. Okay, and well, then I also have 0 if, well, this condition holds, TP is equal to SQ, and TQ is not equal to SR. And then, of course, I also have a 0 if TP is not equal to SQ. But here I would like you to notice the following thing. I'm not saying anything whether T of Q is equal to S of R or not. So if you want, you can just write it in the following way. I can add one more 0 and say here TP is not equal to SQ and TQ is equal to SR. Or if TP is not equal to SQ and TQ is not equal to SR, right? So I split this third case into two cases. And now you can see that basically what happens is the following. We have something non-zero chi p q r if both TP equals SQ and TQ equals SR. And then otherwise, if at least one of these equalities fails, at least one, they can both fail, then we have 0. Okay, so this is a way to remember. Because so you just have to remember that we have non-zero if TP is equal to SQ and TQ is equal to SR. Okay. And now let's compute the expression the other way. So now I'm taking M of chi P, M of chi Q, chi R. And as before, I'm making a substitution. So this is M of chi P, chi QR, if T of Q is equal to S of R and 0 otherwise. So if T of Q is not equal to S of R. But now we again unravel what is multiplication of chi P with chi QR. So again, we do the cases. And now we get chi P QR as before. But now our condition is that the end of P is the beginning of QR, but the beginning of QR is the beginning of Q. So we have two equalities. So if TQ is equal to SR and, as I said, TP is equal to S of QR, which is S of Q. Okay, so we have these two equalities. TP is S of Q and TQ is S of R. And of course, 0 if TQ is not equal to S of R. Sorry, no. I wanted to do it differently. If TQ is equal to S of R, but TP is not equal to S of Q. So that's just unraveling the first line, and we still have the third line. So 0 if TQ is not equal to S of R. But as before, I can just, because here I don't care about what happens with the equality TP equals S of Q. So I have two cases, and I can just split it into these two cases. I write 0 if TQ is not SR. And once I will say, aha, so TP is equal to SQ. And sorry, this was supposed to be end. And TP is not equal to SQ. So see, as before, basically what happens is that the condition to get something non-zero is TQ of equal to SR and TP equal to SQ. So that's exactly as before, and the other condition is just saying otherwise. Okay, so we have equality. This ends the proof. We have an algebra structure.
Sir, may I ask you a question?
No, go ahead, Shao.
Yeah, it is right that the opposite algebra of the graph algebra is equal to the graph algebra of the opposite graph. Is it true?
Yeah, actually, I have such a statement. Since you mentioned it right now, I can write it. This is an equality which is good to bear in mind. If I take K E of the opposite graph, okay, so something like this, and this is the same as taking the path algebra and then taking the opposite of the path algebra. And it's basically that tautology. I mean, you don't have to prove it. I think it's obvious.
Okay, so then I have a next question. So we have already defined the union and the intersection of two graphs.
Yes.
My question is, so is a pullback of two graphs. So the graph algebra of the intersection of two graphs is equal to the pullback of the graph algebra.
Well, hold your horses, Shao. In fact, in the case when the intersection is trivial and we decompose a graph into two disconnected pieces, then this is quite a nice theorem to prove that the path algebra of such a graph is equal to the direct sum of such path algebras. But actually, the difficult part is to prove is that if you have, and this is the theorem of the day, maybe I'll at least manage to state it. We still have 33 minutes. Talking about path algebras of pullbacks or unions and so on, that's definitely not for today. Today, I just want to phrase for you a theorem when E decomposes into disjoint union of two graphs. Yeah, then I have that KE is equal to KE1 direct sum KE2. And this means as algebras. So this means that KE1 and KE2 are ideals in KE. Okay, so knowing this is proving this is very easy. But what is not easy is to prove that if KE decomposes as direct sum of algebras, then E decomposes like this. Okay, this is a nice theorem which I spent the night proving. So it's about I don't know, almost a page or more than half a page of the proof. But I doubt I'll prove it today for you, but maybe I will at least state it. So yeah, so this was an easy question. This is immediate, and I plan to say it anyway. So I just said it a little bit earlier. And this is a far more refined discussion, which I save for later on. And the question, like, what do we do with the path algebras of push-outs of graphs and so on and so forth? This is yet another discussion. And to be honest, I've never seen anybody studying it. We studied it for Levitt path algebras. Our theorems are for Levitt path algebras and for graph sister algebras. And this is where we need all these admissibility conditions which we unraveled in the previous semester. But maybe there is something very simple and natural for push-outs of graphs and path algebras. I don't know. I'll have a look. Yeah, but that's not for today. For today, there is this question of your algebra being simple. This is very important, right? When you have an algebra, this is important whether or not you can decompose it non-trivial like this. In fact, there's a name for it. You say that an algebra is connected if it cannot be decomposed like this, as a direct sum of its subalgebras, with both of them are non-zero. So that's an important concept when you classify things and so on. And it's beautiful that the concept of a connectedness of a path algebra is really tantamount to the concept of the connectedness of a graph. But the very concept of a connectedness of a graph has two theorems associated with it. So this is again a long story which I'm going to do, but not now. Okay, so this time I will do the magic trick and I clear all drawings. And yeah, we continue with path algebras. So Shah, how about I answer your question? Right, I mean, I owe you a formal definition. Let me be any graph. The above constructed algebra which is what? I have my vector space KE with the addition and 0 from this vector space and the multiplication map, which I just defined. This algebra, which you just constructed, is called a path algebra. Or if you want, it's called the path algebra of the graph E. Okay, here we go. We have a first hero, path algebra. A very important concept, as I said, and you can think about it as a generalization of tensor algebras. We're going to do examples in a second. And if you remember your algebraic courses on associative algebras, you know that every associative algebra is a quotient of a tensor algebra by some ideal. Okay, so every associative algebra is a quotient of a tensor algebra by an ideal. But tensor algebras are just very specific path algebras for very specific easy graphs, Hawaiian earrings. Okay. And somehow the idea behind path algebras is that you can sneak in a far more complicated and useful combinatorics when instead of having a Hawaiian earring graph, you have an arbitrary graph. And this is why it's so useful in classification of finite dimensional algebras, not C-star algebras, and in representation theories, okay? Because somehow you will get hold of combinatorics by speaking arbitrary graphs. Graphs allow you to encode combinatorics. That is behind your algebras or representation theory of your algebras. So modules of your given algebra. Okay, now we have a definition, and we already said that K of E opposite is K of E opposite. There is one more immediate observation, that by construction, the dimension of a path algebra is equal to the number of elements in the set of all finite paths. Okay, that's by construction. Because basically what the path algebra is we take the set of all finite paths, we linearize it by a field K, and then we multiply paths by concatenation. So this is maybe not very rigorous, but this is really what's happening. Okay, so obviously by construction, the dimension of your path algebra is just the number of all finite paths. So that's why, for instance, the study of how many we have finite paths in a given graph is actually the study of the dimension of the path algebra. Good. Let's do some more elementary facts, but maybe I'll do it on the next page. Yeah, my elementary facts in the lecture notes are like frequently asked questions, right? Whenever you go to any site, I don't know, embassy, whatever, you always have these frequently asked questions, and then you have some obvious questions and obvious answers. So for me, these are elementary facts. Okay, I can state it as one sentence, actually. and in this famous blue book. You see, the Bible of path algebras is the book which is, of course, listed on our Moodle site. It's called what? The Representation Theory of Associative Algebras. It's a blue book by Simpson, Skowroński, and there's one other non-Polish name which I just can never remember. It's really embarrassing. I always forget this name. And this is really the Bible of path algebras. It's I don't know, like 500 pages long, and it has zillions of examples, and things I'm telling you right now are from this book. And in fact, what I write now as elementary facts is one lemma in this book. Okay, so what are they? The path algebra KE is 1, finite dimensional, if and only if E is finite and acyclic. And now let's see why. Okay, so if the path algebra is finite dimensional, it means that the set of all finite paths is finite. And remember, I showed you a theorem. Well, okay. If for starters, if E, of course, if E is finite dimensional, it means that the set of all finite paths is finite. So in particular, the graph must be finite, because remember, the set of all vertices is the set of all zero length paths. The set of all edges is the set of all length 1 paths. So if a graph would be infinite, we already have infinitely many paths of length less or equal than 1. Okay. So it's obvious that if the set of all finite paths is finite, the graph is finite. This is immediate. Okay. So this is why we can immediately say that E is finite. And then we have a theorem that says that that if E is a finite graph, which we already showed, then the set of all finite paths in this graph is finite if and only if E is acyclic. That's a simple theorem which we had at the beginning of the lecture. So we have an implication one way from finite dimensional to finite and acyclic. And the other way around, we use this theorem again, but if E is finite and acyclic, then by this theorem, the set of all finite paths is finite, and therefore the path algebra is finite dimensional. Okay, so basically what's behind it is the theorem from the previous semester. Next, it is unital, and the unit is the sum over all vertices of chi v, if and only if E0 is finite. And remarkably enough, the same is true when you go to Levitt path algebras and to graph sister algebras. So some things do not change. With a dimension, you have to be a bit careful, because on one hand side, it go into the extended graph by then quotient by relations. So a basis theorem for Levitt path algebras is far more sophisticated, right? I know this is something which you really have to prove by 1 or 2 pages. And you really have to look a bit carefully as to what it is. I mean, it's relatively easy to have a spanning set, but then you really have to throw out some paths in order to get linear independence. But here it's just given to you on the table. But when it comes to unitality, that's the same story, whether you talk path algebras, Levitt path algebras, or graph sister algebras. The unit is always, if it exists, it's just the sum of all idempotents. Because of course you can see, it goes without saying that chi v squared is equal to chi v, okay? That's just by the definition of multiplication by algebra. So all these chi-v's are idempotent, and they're also mutual orthogonal, because if v is different from w, then chi-v times chi-w is equal to 0. So this is the set of mutually orthogonal idempotents. So of course, again, itself is an idempotent, is always an idempotent, but if you sum over all vertices, is actually the identity in the algebra. Okay, and I leave it to you as an exercise, but not for the next week. The next week, I want us to do some things on graphs, and maybe time permitting, Anya will do a mini course about what are algebras, rings, modules, and representation, stuff like this. Okay, and what is the third elementary fact I want to speak about? Well, when it's commutative. Commutative. If and only if. And interestingly enough, you have two cases. So either you have no edges, so E1 is the empty set, or you have edges, but they are very special. So, or each edge is a loop. Based at a different vertex. Okay, so I have, say, one loop, another loop. I can have infinitely many loops. Okay. For such a graph, this is a very disconnected graph. It's also commutative. And it's clear because whenever you multiply any loops, you'll just get 0, because they never end and start at the same point. Okay. And of course, whenever you multiply a loop with itself, that's commutative. It's like polynomials. So this is something funny. This is like commutative polynomials in as many variables, as many loops you've got, but you don't have any cross terms. So xi times xj is equal to 0 unless I is equal to j. So somehow these variables annihilate each other. But then it's clear by the theorem we're going to prove this is a disconnected graph. So I can just write it down as a direct sum of polynomial algebras in one variable. Yeah. And this is obviously commutative. So it's not a polynomial, commutative algebra of polynomials in n variables. No, because if I have two commuting variables x and y, then x squared times y is non-zero. But here x times y is always 0. So that's the story. And this is again an exercise, a nice exercise. I mean, both are nice exercises. And there, oops. Oh, I went back. So you can go back. It's so nice. These are very nice exercises because on one hand side they are elementary, but on the other hand they show you how things work. So I will ask some of you to do it in 2 weeks. Okay. So I want you to have some fun, and I will not prove to you everything. Some things you have to prove yourself. Okay. Now after elementary facts, let's do elementary examples. They're really basic examples. Okay. So we understand what to eat it with. So first, function algebras. If there are no arrows, so if E1 is empty, then KE, well, you can guess this is the space of all finitely supported maps from, sorry, E0 to K. As an algebra with pointwise multiplication. So with pointwise addition and multiplication. And I'm not even writing it as an isomorphism, I'm writing it as an equality, because remember we defined the space, our vector space KE as the space of all finitely, so this F means for finitely supported, okay, this F. Of course, if you have a topological field like real numbers or complex numbers, you can also say these are functions vanishing at infinity, right? Because we have discrete topology on E0, and in discrete topology, the only compact set is finite. So I'm only talking about functions that vanish outside the compact set, which means they vanish outside the finite set, which means they are finitely supported. Okay, so this F stands for finitely supported. And they agree on the nose, because you have this characteristic functions chi p, and if you have two functions with disjoint supports, they multiply to 0. If they have the same support at one point, well, then they multiply to itself. These are idempotents. And thus you see that if you look at the basis of the right-hand side, this is the same as the basis on the left-hand side, and the pointwise multiplication on the right-hand side agrees with this Kronecker delta multiplication on the left-hand side. So we have equality on the nose. It's not even an isomorphism, okay? Because of the way we defined KE. Okay, so that's clear. So in particular, if E0 is finite, well, that's a unit of algebra. And you have all functions on E0, and of course we have the unit map. But you see that if E0 is not finite, then this algebra is not unital, because the unit map assigning 1 to all elements E0 is not in my space. Okay. So this is sort of the most boring case where you are doing nothing but finally supported functions on a set. Okay, so let's make it a bit more fun and talk about matrix algebras. So now we take the following graph, E. That is garbage, let's erase it. Let's say that I have n vertices, v1, v2, up to vn. And between any two consecutive vertices, there is exactly one edge, and it goes from the vertex with a smaller number to the vertex with a bigger number. So there is only one edge from vi to vi plus 1, and there are no other edges. So if you want to have just this one path of length n, okay? Second, for instance, immediately compute the dimension, right? Because it'll be 1 plus 2 plus 3 up to n. Because we have n vertices, so n paths of length 0. We have n minus 1 paths of length 1. We have n minus 2 paths of length 2, because we can where we can start, and so on and so forth. Or if you want to count from the other end, we have exactly one path of length n. We have exactly 2 paths of length 2, because we can start at v1 or v2. We have 3 paths of length n minus 3, because we can start at v1, v2, or v3, and so on and so forth. And finally, we have n paths of length 0. So I'm just summing from 1 to n, and that's the dimension of this path algebra. But this is also the dimension of the upper triangular matrix algebra. Okay, so I claim that KE, well, this identification is natural, but it is an identification, so I'll write it as an isomorphism. And I call it UT, upper triangular n by n matrices over my field K. So by definition, I mean all matrices of size n over the field K with a property that Mij is equal to 0 for any I less or equal. I wanted upper or lower triangle. I wanted upper, so for I bigger than j. Yeah, because if the row number is bigger than the column number, you are below the diagonal. Okay. Okay, so I claim that we have such an isomorphism. Let me specify it. So on my left-hand side, my basis is, so how do I do it? I specify first the linear map from KE into UT and K, right? From the left to right. So this will be implemented by the map F. And for starters, it has to be a linear map. So I better assign to all basis elements on the left, something on the right. But actually what I'm going to do it, I'm going to assign to basis elements on the left, basis elements on the right. So you'll immediately get that this is an isomorphism of vector spaces. And then you have to verify that it actually obeys, it's just an algebra homomorphism, okay? But let me write it down. So I take chi Pij, where Pij is the unique path from my vertex Vi to vertex Vj when I is less or equal to j, okay? I'll write it down later on, but first let me write this assignment. I call it F, and I map it to an elementary matrix, Eij. Okay, so let me explain it, the notation. So where Pij, well, maybe first let me make sure that we remember that I is always, less. Less or equal to j. You see, if I is bigger than j, I have 0. Nothing happens, okay? There is no going back. If you have a vertex with a bigger index, then there's no going back to a vertex with a smaller index, okay? And I look at my matrix elements. If I is bigger than j, then it's the Mij is simply 0, okay? So I'm interested in the opposite situation to this one. So when I is less or equal to j, okay? And then Pij is the unique path from Vi to Vj. Oops. From Vi to Vj. I have to go to the next page. These Eij's are elementary matrices. So Eij is a matrix. So I can take its matrix elements, say Lm, and by definition, this is given by two Kronecker deltas. So I have delta IL, delta Jm. So in other words, this is a matrix which has zeros everywhere except when I look at ith row and jth column, and at this spot I have a 1, and everywhere else I have 0. Okay, that's the elementary matrix. So I explained the notation, and you already see that now it's an isomorphism of vector spaces, right? Because you basically map one basis to another basis, so you are good. So that now we just need to verify that when I take f of chi Pij times chi of PLM, I want to show that this is a homomorphism, okay? Of course, it suffices to do it on these basis elements, right? Because these are all paths. If you look at all finite paths for this graph E, then these are just paths from some vertex Vi to some vertex Vj. And of course, when I is equal to j, then the path is this vertex itself. So we are not losing paths of length here, okay? But now, first, let's multiply it. So obviously, this multiplication is 0 unless j is equal to L, right? Because then Pij ends where PLM starts. So I can write Kroneker's delta JL, and then Pij times PLM when j is equal to L is of course PIM. So this is f of chi of PIM. And of course, this is just delta JL by definition of F, and the elementary matrix EIM. But of course, how do we multiply elementary matrices? So let's take EIJ times ELM. So it's obvious that, why do I have this? This is spurious, okay? So it's obvious that if j is not equal to L, it's going to be 0, because by the rule of multiplying matrices, this unique one which is in the left matrix will always miss the unique one which is in the other matrix, okay? So of course we must have delta JL, but when we have it, then of course there will be one non-zero entry, which will be precisely when I take my ith row in the first matrix and multiply it by the jth column in the other matrix. Then the ones will meet because I assume that j is equal to L, okay, and it's exactly this formula. But now, of course, this is this is precisely f of chi Pij, f of chi PLM. So this way we prove that this assignment f is indeed an algebra homomorphism. So if you just have such a straight, simple path from V1 to Vn, and have n vertices, then you have n by n upper triangle matrices. This is exactly this algebra. And maybe let me do a spoiler here. Many of you probably know very well that if you now go to Levitt, path algebras or graph system algebras, this here the same, because for finite dimensional case, there's no difference between Levitt and path algebra and the graph system algebra. Like whenever you have a finite dimensional Hopf algebra, semi-simple, it's completion into a compact quantum group sister algebra is the same Hopf algebra again. So this will be full matrix algebra, and that's because of but this is no longer so obvious. This is a bit tricky because here it's completely elementary because our basis is elementary. But if you want to prove, say, that the Levitt path algebra of such a graph, which we just used, is the full matrix algebra, you have to have a basis theorem. You cannot do it otherwise. There is no shortcut. Okay. And spanning is no problem, but you have to prove as an isomorphism. And you have these relations, and they are non-trivial. They're Kunz-Krieger relations. They are non-trivial. So if you really want to prove that this is an isomorphism, you have to use a basis theorem for Levitt path algebras. But then, roughly speaking, you can understand what's going on, because here another spoiler alert. When you define a Levitt path algebra, you'll take the extended graph. So you'll take the graph, you'll take the opposite graph, and you will glue these two graphs over the set of edges, vertices. Sorry, not edges. So sort of you have the same vertices, but every arrow has the ghost arrow going in the opposite direction. And this is exactly like having a conjugate. And this is what happened with matrices. Now for everything which is in the upper right corner, you have something corresponding in the lower left corner. And this is why you upgrade from the algebra of upper triangular matrices to the algebra of all matrices. Okay. So this already shows that somehow, in a way, Leavitt-Pav algebras are nicer than Pav algebras because you get full matrix algebras. We have many, many important algebras as Leavitt-Pav algebras. Okay. But this is also not too bad. We have upper triangular, the algebra of upper triangular matrices. Oops, and the time is up basically. Wow, so this is really slow. I have 2 more examples to do. So maybe let me still do these 2 examples, okay? And yeah, let's do these 2 examples so that we stop before the theorem, okay? I want to finish examples. Now the 3rd example, which I want to give you, is well, the polynomial algebra in 1 variable. But I want to make the following statement. It's very important to me that you must distinguish polynomial algebras from polynomial function algebras. For many typical fields, it's all right if you have characteristic 0 and so on. But if you take some finite field, then it is not true that the function algebra, the polynomial function algebra, is the same as the polynomial algebra. The polynomial algebras are defined, and if you, it's usually done very badly in algebra books for students. But there is one beautiful book, Serge Lang, Algebra for graduate students, and their polynomials are defined properly. These are convolution rings. For any monoid, okay, you can define the convolution ring of this monoid by taking all finitely supported functions from your monoid to your coefficient ring. It can be any ring. And you define the convolution product. And in particular, if you take your coefficient ring to be, say, your field K, and if you take a monoid to be a monoid of natural numbers, you get exactly the polynomial algebra in 1 variable. Okay, this is the convolution algebra. And this convolution algebra is exactly the same as the path algebra of a graph consisting of just 1 loop, 1 vertex and 1 loop. So I just write a not polynomial function. Because mind you, I didn't assume that K is of characteristic 0 and so on. Not polynomial function algebra. Okay. So now my graph E is very simple. I have 1 edge, which is a loop, and 1 vertex, so V and E. And that's it. Okay, so now K E is just equal to Kn. I use this notation to remind you that this is a polynomial algebra, not polynomial function algebra. But of course, it's very common to just write it as K of X. X you can define as an appropriate function on natural numbers, okay? And you can view it as your independent variable. It's easier for notation. And here is obvious how you write it down. Again, it's a canonical identification, so I write it as equality, not an isomorphism. So if you take this unique vertex V, then chi V, of course, goes to 1. Remember, this is unit, or what is the unit of a path algebra with finitely many edges? It's the sum of all idempotents corresponding to these edges. But here it's just 1 idempotent, so the sum is just chi V. So chi V is 1, okay? So chi V is 1 in our algebra. So of course it must go to 1, but 1 is just x to the power 0. Okay, this is how you can denote it. Okay. And for positive integers, of course you take chi En, because all your paths will be just powers of your loop E. There are no other paths. There's a vertex V, and then there are some positive powers of E. That's it. This is your basis. Okay, and of course you map it into Xn. Okay. And again, because here the only identification we make is a very simple identification. I identify my path with its length, but here I can do it, right? Because all I can have, if I view V as the 0th power of the edge E, then basically I'm identifying all finite paths with their length. But this is identifying all finite paths with natural numbers. And when these are functions finitely support natural numbers, and these are functions finitely supported natural numbers, left and right are the same. So this is the canonical identification. Okay, so I write it as equality. Okay, so that's this is important. This is of course commutative. And there is one more example which is very motivating, namely tensor algebras. Or if you want, non-commutative polynomial algebras. Okay, so now our graph is the Hawaiian earring. Anya, do you have Hawaiian earrings? With your jewelry. This is very nice. You have, it looks like this. You have one loop, you have another loop, and so on. So take n loops, but they're all based in one place, right? So this is called the Hawaiian earring. I like the name. It's somehow very telling. Okay, so I take such a graph E, and now I claim that the path algebra is isomorphic with the tensor algebra of a vector space V. And let me remind you that the tensor algebra of a vector space is the following algebra. You have K plus, and then you take all positive integers, and you take all tensor powers of V, okay? Sorry, I should give a different, let it be M, because here I just want to label it, these loops E1 up to En, okay? So N is for the number of loops, and if you want, it's the same as the dimension. Well, maybe I may, let me still write it down as, oops, I forgot, this is a plus. Sorry. Yeah, because I mean, I can write it as V to the tensor power 0, right? But that's not so obvious what it means, the 0th tensor power. So I write it separately. And you can also view it as with non-commutative polynomial algebra. So this is used with these pointed brackets. So you have x1 to xn, you have n independent variables, which are completely non-commutative, okay? Yes, and here, if you want, n is the dimension of V. Okay. So remember, I told you that tensor algebras are these universal algebras, giving you any associative algebra as a quotient of a tensor algebra. And now you see that the tensor algebra is a path algebra for the Hawaiian earring graph. So by doing path algebras, we are just introducing some very non-trivial combinatorics into a very universal construction. And in fact, these are not path algebras people are ever interested in. That's not really the point. The whole story about path algebras is to study quotients of path algebras by appropriate ideas. And people who do representation theory and classification of finite dimensional algebras study so-called bounded ideals in path algebras. And then they can present, given a finite dimensional algebra of a field K with some properties, they can construct so-called Gabriel quiver or Gabriel directed graph, and then can take the path algebra of this Gabriel graph, and then there exists, not uniquely, but there exists a bounded ideal such that your given finite dimensional algebra is just the quotient of the path algebra of the Gabriel quiver by a bounded ideal. Okay. And we are going to do something very similar, except that first we have to do the extended graph. So to every arrow, we also associate the ghost arrow. Then we take the path algebra of the extended graph and divide it by the constant relations. Okay. So we are always interested in quotients of path algebras, not in path algebras themselves. That's why probably Shao, nobody looks at such questions. What is the path algebra of a Pushal and so on? Because in a way, who cares about path algebras in themselves? They are vehicles for constructing, for presenting other interesting algebras as quotients. Yeah? And it's quite remarkable how many sister algebras in non-commutative topology, quantum groups and so on, come as graph sister algebras. And I already said it in the previous semester, but you cannot overemphasize it, that raison d'etre of graph sister algebras is to unravel their K theory. So if you really want to do something non-trivial with non-commutative topology, you might as well start with K theory and then presenting your favorite sister algebra that you want to study, which comes, for instance, from quantum groups or any other constructions, have some geometrical roots. If you can present it, which is very non-trivial, as a graph sister algebra, typically very non-trivial, then basically you have its K theory on the plate. Okay. All right, and just to finish, I think I still have to give you this identification, right? So, but you can easily guess it. I'm taking chi of EI1 ... EIM. Yes. Because the any path for this graph is just a word written in these loops. And because they all end and begin at the same point, obviously, and of course the algebra is unital. So if you want chi of V, maybe I should write it first. Of course, chi of V goes to 1. Yeah, and this 1 is remember in this field K in the tensor algebra. Sorry. I view field K as a subset in TV. Okay. So that's obvious. But now let's take a path which is of non-zero length. And then, of course, this is just a word written in terms of these loops and loops. And you can guess where I map it to. I map it to, let me write it down and then explain the notation. I simply map it to F I1 tensor ... tensor F IM, where for starters, the sequence I1 to IM is simply an element of a Cartesian square of numbers. So I have a set from 1 to n, and I take it to the nth power. So in other words, this sequence of IM to IM is an arbitrary sequence of numbers from 1 to n. Okay. And then, of course, you have all basis elements for KE, given as K chi EI1 ... up to EIM, except, of course, for chi V, but we already handled it. And now this set Fj, with J ranging from 1 to n, is a basis of V. Remember, we wrote that the dimension of V is equal to the numbers of loops in our Hawaiian theory. Okay. So you have a perfect match. So you take the same sequence of numbers from 1 to n. So each of them chooses a particular basis vectors in our basis. Can be any, so you see, so this depends on the basis. So this identification is not canonical, okay? That's why I write it as an isomorphism. But it is an isomorphism, and it's completely obvious that it's an isomorphism of algebras, because if you multiply chi with one word times chi with another word, then you'll just join the words. You can always do them because it's just one vertex, so they're always compatible. There are no zeros around. And of course, how do you multiply in tensor algebra? You have one tensor and you multiply it with another tensor. In what way? By putting a tensor product in between, right? The multiplication of a tensor algebra is, of course, the tensor product. When's the name? So it agrees. It's always an algebra isomorphism. There's nothing to check. And I think that this is a good point to stop, because the next thing is this theorem. We just spent the night proving, and I will not have time even to state it. Okay, we took 15 minutes away, so let's meet again in half an hour. So say 29 minutes. Let's meet 11:45. Okay, so we have 29-minute break. I stop the recording.